Hello, this is Tommy Henderson, and I'm here to cover updates in low noise amplifier and devices past and present. So we'll look at several different designs, and then we'll make some comparisons of what has happened over the decades and what kind of devices do we expect to see in the future, and what the noise figures of those look like. So let us begin. So in the beginning, if we look, this is 1968, and I just put this up here so you can get an idea what device and stuff looks like. We had bipolars then, and 3 dB noise figure was actually pretty good from a device, and you can see the type of matching sections that had to be developed in here to get these things to work. So keep in mind the devices themselves weren't anywhere near the noise figures we have today, so we had to do extra stuff on the input matching, maybe silver plate them, maybe use a higher cued piece of metal here over a larger area. We had to do something to compete, to make things lower to help out the devices, because inherently devices weren't that great yet. So let's jump forward 10 years. Let's look at 1978, and we can see, other than this abnormal number here, we can see most everything was in the 1 to 1.5 dB noise figure range, and we can see there's a good variety of devices here, some bipolars, a lot of FETs, the 3 and 211. I recall using that device quite often in the early 80s. So U310, I think there was also a J310, so that was another device that was used quite often. Again, then that's about the noise figure we would expect out of them, is between 2 and 1/2 and 2 dB. Nothing really fancy. In the same way, the MRF 901, that was another device used a lot for small stage gain or buffer amplifiers. Not really that great of a bipolar for noise figure, but it wasn't that bad. And if we come over here to 432, we can see that the 1.5 was about the lowest, and anywhere from 1.5 to 3 was pretty standard. And that's what happened in 78 until the gas FETs became more popular. So some of the early gas FETs were the D432, DXL 2501, and the MGF 1400. And so you recall W6PO produced these for the iMac notes. I still have my iMac notes. And now this is the 2-meter version with a Series L and a little parallel resonant circuit here to match to the device, and used a 4-to-1 balun for the output. And here's a strip line version for the 432. Fairly low loss, a little low losses than using a coil. Using a strip line gave you a higher Q, and also a microstrip version of the same type of amplifier. We have a device here, there's a blocking cap, so we have some matching sections. And these the microstrip at that time would be a little bit higher noise figure than the strip line for frequencies below 500, 600 megahertz. Here's a version. This is a dual gate version that I put together in '85, and one of the neat things about the dual gate is it had a better IMD performance, and you can really tell that on terrestrial signals, that sometimes the dual gate would outperform the lower noise single gate. The noise figure weren't that far apart, but the performance here may have been a little bit better. And so I threw this picture, still have this LNA in the junk box, and there's the 3SK 174 dual gate. So here's some of the single gates that they had in '84, and here's some of the dual gates. Likewise, 70 centimeter design by N6CA. This was very popular, and again, we're just showing the variety of different type of circuits. Here we use an inductive match for the gate, which matches quite nicely, by the way, but this is very broad banded, so to provide a high pass circuit, would ensure that maybe the lower frequencies, 2 meter or 6 meter, would not be amplified and get into your receiver as much. And here we're using a variety of matching circuits, maybe a little resonant circuit here terminated to 50 ohm to help bypass the lower and upper frequencies. So we get some frequency response with this little circuit too, and a small matching circuit. And it's a fairly stable circuit and was quite popular in those days. So let's jump ahead another 10 years, approximately 1986, and all my information comes from Central States VHF and Above noise figure competitions. And you can see in at this time frame, now gas FETs are pretty prominent in the lower noise figure. And see, we've dropped from 1 dB down to well below half a dB noise figure on 2 meter. And you can see the devices. There's one of my older 1202s, but they performed quite well. And on 1296. 1402s were the main one. 1412 is an excellent device, and still have spares of those in a box. Hasn't been touched in a while, but I still like them, so they sit there just quite nicely in a box. But they were about a half a dB noise figure at 1296. So in order to get lower noise figures from 2 meter up through 23 centimeter to a point, we decided that several people come to find out that thought, let's just lower the line losses and develop cavities. So more and more cavities were being produced, and like I show here, this is a 222 cavity. This is a 70 centimeter cavity. This uses capacitive coupling, uses inductive coupling. Here's one that I've broke apart for you to see, and silver plating everything also helps a tiny bit. With devices at that time, it probably helped a little bit more, but with devices going lower and lower in noise figure nowadays, all this added work may not show itself on a noise figure system like it did back then. Again, we're making a device that's really good, make it look really, really better, where today the noise figures are so low that all this extra work may not show up as easily on a noise figure machine. Refinements and gas FETs technology in the 80s. Here is a Vontech come out with their gas FET, and here's a real stable design developed by W5LUA, and again using an inductive match like we've seen before, and a fairly stable design, and consistently half a dB noise figure at that time. But not soon after that, the HEMT technology started taking hold, and those were produced in the very late 80s, early 90s, and they will be the mainstay now throughout the next 2 or 3 decades. So here is one that was introduced. The 4303 is the one that I used, and so this is a circuit I produced in around 1990-ish, some of that time frame. And fairly simple design. Did use some resistive elements in the drain lead to help stabilize the circuit. But this is a fairly stable circuit. You can omit the 270. I feed this into a second stage. The second stage provides some good stability. Anyway, this circuit would do 0.4 dB noise figure and 0.2 dB cooled in a liquid nitrogen bath. That led to a 2-stage design, and here's a more updated device. Use the NEC device at this time, the 32584 and the 32484 both during this time frame, and followed by the I guess about this time is a Vago ATF 21186 second stage, which was a larger micron gate, a little more stable device than running 2 HEMTs. That usually was a disaster, putting this HEMT here, a lot of instability, so this device is much more stable. And I show it here as a negative controlled bias on the device, but anymore this second stage can just be self-biased and it works just fine. The first stage is still negative, has a negative gate bias and a complete shorted source lead via some inductive feedback to help with stability. And this would consistently be low .3s at 28 to 30 dB a gain. So if we review what we've looked at so far, we worry about stability, so we want to have a K above 1 down here, and this right here is our gain and our noise figures. So here noise figures are below half a dB, and our K is above 1. There's a little below 1 up here, but that's so high in frequency, above 16 gigahertz. I doubt the device has much gain there, so I'm really concerned about from here to 10 gig, and that's the circuit we just showed you. So ways to help with that would be very particular about what you use for your matching. The input for low frequencies, again, I would not go above 500-600 megahertz with this type of input circuit. On occasion, I might do a 1296 with a cavity input, and the cavity inputs on 1296 don't do any lower noise figure, at least in my lab, that an inductive match like we see down here. So we get nearly the same noise figure here as we do up here on 1296. However, on frequencies of 432 and 2 meter, then this circuit here is still, to me, better because, first of all, the bandpass support you get here, where this just lets everything in, and at those frequencies, it's just not a good idea. So below 500, 600 meg, this works very well, and you can either do a capacitive input with a parallel circuit here, or do a tapped input with a parallel circuit here. And it just depends on what the application is, but I do a lot of tapped inputs and do away with this capacitor. Again, I'm self-biasing below 500 megahertz. I don't mess with negative bias. And as we saw in the early days, people were using 4-to-1 transformers. Those are not used as much anymore due to the instability with the newer HEMT devices. So you really get a lot of gain here, and the impedance is not too bad, but a lot of instability with all the gain, and it just doesn't work as well as maybe doing this circuit here, or adding a diplexer circuit on the end of this one. So that's why I show this circuit here on the bottom is pretty much what we do now on anything of 2 meters and above. A little bit of series R in the neighborhood of 20 to 30 ohms, and a small amount of inductance here, not a large inductor here, somewhere in the 100 to 200 nanohenry, and maybe a 30 to 40 ohm resistor here for broadband loading. And but if this is not stable enough, or you need a little more bandpass circuitry, then this output would then feed the diplexer, and this terminates all the lower frequencies and a higher frequency in the 50 ohm, as you see here, and then the resonant frequency would go through this series resonant here to the output. So that's our preferred circuit in place of a 4-to-1 balun, is this circuit here along with this. And the microstrip and L match is good, basically above 1 gigahertz. So anything above 1 gigahertz to 3 gigahertz we can match with an inductor here. Above 3 gigahertz you cannot get a match properly and need to go to some sort of microstrip. So we put a microstrip here, and again we're using ground source at those frequencies. So let's jump ahead another 10 years to 1996. We can see now with people discovering that a power FET gives us better IMD performance and inherently even lower noise figure. You can see some of those in the table, but pretty much the same crowd as far as the 1302s. And then down here we can see how the HEMTs are really taking over on 1 gigahertz and above. Everything here but this 1412 is a HEMT, so that's a gas FET, that's a gas FET. But you can see the lower noise figure with the HEMT devices. This is a test fixture for a 2.3 gigahertz design, and so I I pin the device in there, use some simple inductive match, and so the following table was using this circuitry. And so here you go, this is in 2008, and here is all the devices, and here are the specified by the manufacturer, and this is what was measured. And of course everything measured is always higher than what the manufacturer says it'll do, but some of them are pretty close. And the sad thing is most of these devices are no longer available. So mark those 3 or 4, 5, 6 off the list. That one's no longer available. So the only one out of this whole category here that's available is the 4953, and the newer version of the NEC would be a CE. So it'd be a CE or 3512 or 14 or something like that. I have it on the next slide. So those two are the only one being manufactured. All these have been obsolete now. So here you go. Here's 55 years of low noise devices. I started off with some of the early bipolars, made our way to the MOSFETs, down in here to the GASFETs in the early 80s, all the way through to the beginning of the GASFETs in the early 90s, to the our HEMTs, to the current HEMTs right here. There's the two right there that are currently the only ones I know being manufactured. And then the MMIC device, which I'll explain here in a minute, these are the two current MMIC devices that we show. So after 2000, a shift to more stable designs, maybe higher IP devices. So Avago had the 54143. These were really great devices, and I still use those, but they're no longer being manufactured. So obviously I'm getting them wholesale through various outlets, and they had between a 1600 micron and 800 micron gate. Very stable in most designs. I mean, they can still become unstable, but they're mostly stable and had very high IP, like the 33143 can easily do plus 13 P1 dB in an amplifier actual circuit. So those were great devices. And then here's some other devices. Again, all these are no longer manufactured, but all these would provide fairly great IP performance and give you fairly decent noise figure. So we go to MMIC devices, and these are the ones that are currently being manufactured I'm familiar with. And of course the one that jumps out the most is the PGA 103 by Mini Circuits, and its complement is SPF 5189. Z is a manufacturer. Probably both the same dies. They both do about the same, have the same perimeters. I put pluses to those because I like the device casing in that. All these others, the Sky 57183, this one here, the BGU, and the TQP, all use nasty, well, I call them nasty, hard to work with case mountings, device mountings, which I'll show you here in a minute. But if we look at the noise figures, they're actually quite impressive. Not quite as good as the HEMT devices, but not too far off from it. And if you cryogenically cool these, which I've done a couple of them, you are at about near the same noise figure as a room temperature FET. So like the 0.6 can easily get down to 0.3 once it's cooled in a nitrogen bath. Here are the device cases I was mentioning. I call it the great, the good, and I don't mean fair. Fair is, it's okay. So great, good, fair, okay, and just flat out ugly. So you can recall the Micro X we used there in the 80s and 90s, and then we transitioned over to the SOT89, which is still a good way to solder a device down. And then the SOT343. Again, this is not a bad device. I can see that one just fine with some readers. But boy, I'm not. These right here are just very difficult to work with, and if you do, that's great. But you're on your own on these. This is the DFN or QFN devices, and those are what a lot of the MMICs are going to. So if we look at the MMIC circuit, just basically you should have a blocking cap here, blocking cap there, input, output. Make sure you have good grounding all the way around it. They're not stable, and increase in noise figure and lower gain when the grounding is poor around them. This is a device operating at 4.8 volts, 100 milliamp for the setup I have for the bias. So it'd be like your PGA 103 if I was running it in this circuit, but it could be anything. I just adjust these resistors. I do like running 8-volt regulators. I do not like running 5-volt regulators on MMICs because some of them run so close to 5, and I do like to put a little bit of resistive loading into here. I like the 10 ohm because I can measure voltage drop easily across the 10 ohm, which in your mind and your head can be converted to current quite easily, right? So 1 volt should be what, 1/10 of an amp or something like that. So it's easy to use that as my current measuring, and also gives me some decoupling between the noise of the regulator and the circuit. So I usually like to run 2 resistors and the bypass for the device versus and a little bit of resistive loading for the inductor. Helps with low frequency stability. Again, you could probably run this right up there and run this inductor a little bit larger in size, like 100, 200 nanohenry. But I like this because I find it more stable with this circuit. That's all. And then if you need, and again, this is wider than a barn door, so I would start with maybe an output matching or output high pass circuit. Or better yet, use mini circuits, drop in SMD filters, which I use quite often. Again, I just use them, so that's the only reason why I mention them. And on this one, this is the input, output, and this is your ground. So you could put a 145 in there and have a LNA that works from basically 144 megahertz and up, or put in a 440 that is good for 70 centimeters and up. So those are a good alternative to have it to design your high pass circuit here. And if if you need it on the input, obviously your noise figure is going to be worsened, but maybe super low loss inductors and capacitors here. Maybe you can do one for under 0.5 dB noise figure, and that would raise your overall noise figure to about 1 dB. But again, not bad for terrestrial use. I just do not use this setup for EME. However, I do use the MMIC as a second stage, and it works just fine. So in conclusions, 70 centimeter, 2 meter 70 centimeter LNAs using gas FETs benefit from high Q front ends, whether it be strip line or cavity, to prevent out-of-band RF from being amplified. However, newer devices require less external parts to achieve low noise figures. So they are already inherently low. You don't have to go through extravagant means to get the lower losses in the front end anymore to have a decent noise figure. 23 centimeter and above, the more simple inductive matching or microstrip for even higher frequencies is proven to be as good a noise figure as any type of cavity. And again, we're talking about hundreds of a dB difference, and it's just not really worth it. Therefore, no updates are required from what I already shown you. Manufacturers are narrowing their selection of HEMT devices available, and they're looking at maybe more and more MMIC devices for their higher IP, broader band performance. And again, when they're cooled, they work great. So, so other than the high IP MMICs, you need filtering that may outperform a HEMT device for general usage under 1 gigahertz. However, they do not currently provide the lowest noise figures for space communication compared to discrete HEMTs, unless they're cooled. A reduction of 1/10 of a dB noise figure earns about 1 dB cold sky to ground on a good EME section or system on 2.3 gigahertz. So I'm going to personally stay to HEMTs above 1 gigahertz and above, but you may have to decide what works best for your application at lower frequencies. So I think our time is up. I was glad talking to you all today about that, and hope the information is useful in your decision making on developing LNAs. So thank you very much. Audio. There we go.
Yeah, I'm sitting here talking away, and I'm on mute here. Anyone have any questions to ask Tommy here? Some really good information. I really enjoyed that very much, especially the challenge you've been going through for quite some time as manufacturers drop components, and you have to go looking for alternatives for all of that. Are you finding anything any simpler by chance as far as newer technology, newer versions that are coming in?
The MMICs are easier to match and easier to get working if it wasn't for the casing styles that you have to mount. So it becomes more of a challenge for us that may not have a full blown surface mount to air type of heating or what we call flow type of soldering that we can get those parts down. So really
Mhm.
that's the challenge. More of a challenge to do that than it is to actually design an LNA.
Oh, my. Wow. Very good. Okay. Any other questions? Please drop them in the chat here. It seems everyone is running into this component shortage, as everyone has been going through for a long time. And I know it's for me personally, it's really tough when you finally get something you really like, and only to find you can't reproduce it, or you're
It
held up.
is, and what we do have, uh, it's hard. They were big.
Oh, lost the audio. Mm, mm. Oh, I think the audio may have frozen there. Let's see. I'm not sure if you're hearing me, Tommy. But let me move a question over here for us. There's a question from Danny, W9 Delta Papa there, it looks like. What device do you like to use for 10 gigahertz? Oh, looks like Tommy must have dropped out there, so apologize for that. But if you do have any other questions, please drop them in the room. We'll in the chat here. We'll try to capture as much as we can, and perhaps we can get a follow up there. Oh, okay. Yeah, I just talked to Tommy. He had a power failure at his place, but he'll be here in just a moment. So if you do have any other questions, please drop them in here. We'll get an answer for you here momentarily.
Ah, is that
There
up?
we go. Welcome back.
Wow. Yeah, that breaker got tripped. So
Oh no. We have one question here. I'm not
all
sure if
right.
you saw this before it dropped out on you
Now,
from
what device
Danny.
should I use on 10 gigahertz?
Mhm.
Um, the if it's a well, it'll be a HEMT. It won't be a mimic. So I don't have any know of any HEMTs or mimics that work at that high frequency. So it's probably going to be that CE 3512 device or the Mitsubishi device. Those are the only two that I know currently that are in a package that I can mount in the Micro X package. And I mean, I know there's others in those other packages that are available, but they're not easily to get. You can get the CE through Mauser, or you can get it from you can get the Mitsubishi from Mitsubishi. So those are components you can actually buy, and they are current devices, and they should be about a half a dB
to 3/4 of a dB noise figure on 10 gigahertz.
All right, very nice. Any other questions? I'm not seeing anything else come back up in there. I guess not seeing any more questions. Anything else you want to mention in closing?
No, I mean, the big thing on if you're going to do a a microwave type circuit, you really need to model how much source inductance you have. At 10 gigahertz, you can probably take that source lead and go right to ground with it. Have virtually no source inductance as it goes to ground, and be just fine. And probably go ahead and do a two-stage if I was going to do one on 10 gigahertz, because at 10 gigahertz, that LNA is only going to have about 8 to 10 dB a gain. So with two up, you'll be up around 20, 22 dB a gain. And that's what I do at 5 gigahertz. It's two stages to get the gain up to where I want it. Most of us on EME try to run 20 plus dB a gain for the LNA at the feed point.
Okay, real good. Looks like we have another question from David, AC2GL. Are there any of the LNA designs available as kits?
No, I do know some people that do produce kits, but I don't know any on stateside that does. We actually build LNAs here, and I can provide you a board if you wanted to. We usually just build them here and test them in the lab here, anywhere from 2 meters on up. So if it's if it's lower frequencies, it'll be either an LC or a cavity circuit, and if it's higher than 1296, it's in some sort of either a strip line or a inductive match type circuit.
Ah, real good. Okay. Any further questions? Okay, I guess I'm not seeing anything else roll in. So I guess me personally, I want to thank you very much, Tommy. I've certainly appreciated it a great deal. I'm sure many others did here as well. And I guess, all right, very good. Well, go ahead and drop the stream here. So thanks everyone for attending. Appreciate your time and joining us today.
All right, thanks.
All the best.